Recording. We're going to solve the position problem, position analysis of this guy. This guy is known as a slider crank. Okay, and it is known as a slider crank because it has a slider and a crank. If you remember from last session, crank means that it is allowed to have a full rotation. So in this case, the crank is that one because it's allowed to have a full rotation, and that's the slider. Okay, now I'm going to copy the diagram because I'll use it again. I'm going to erase that thing. Now, can you think of applications in which you encounter a slider crank? Real life applications, I mean.
Door mechanisms.
Say that again.
Door mechanisms.
Door mechanism, because it has a piston, right? What else?
An oil seesaw.
I think most of these seesaws have a slider crank. Yes, it doesn't matter if it is for oil or not. There's another application which is more common, especially for those who like cars, in which you've encountered the slider crank. ¿Cuál es?
Pistons.
In a piston. Now, in a piston, inside a motor, you have pistons, and the piston behaves as a slider, right? It moves linearly because and it produces the rotation of other things. Entonces tenemos un árbol de levas, ¿sí? Tenemos el pistón. Si se acuerdan o si saben cómo funciona el motor, saben que la cabeza del pistón realmente se mueve de manera lineal y eso hace que gire el árbol de levas, etcétera, etcétera, ¿sí? Bueno, ahí hay otra aplicación. Now, I want you to think of something that is very important, and I'm going to jump to SolidWorks for that. Okay. Now, you know this guy moves like that, right? How many degrees of freedom this one has?
1 degree.
It has 1 degree of freedom. So, and you can validate that by saying, okay, if I fix this one, nothing else is alive anymore. Yeah, so it validates that it has 1 degree of freedom. Now let me release this again. If you are looking at the mechanism in SolidWorks, you can say, okay, I'm going to add a rotary motor, a rotational motor to this link, and then it's going to move, right? Basic stuff, or almost basic. But if you think of the application like in the motor of a car, in the motor of a car, the input is not this one. The input is where?
The piston.
It's through the piston, through the slider, right? Okay, so I want you to think of that because it gives us some general idea of how things are in the real world. So let me say that again. In SolidWorks, this one moves. I can say that this is my input, but there are some applications like the motor of a car in which that guy is the input. And you can simulate that in SolidWorks. You can say, okay, I'm going to add a linear motor to this element so that it moves this way. You see, here I'm controlling the slider and still be able to move the entire mechanism. Entonces tienes dos opciones realmente. O le pones el motor aquí, o le pones el input acá. Ahora, solo se puede una u otra, porque solo tiene un degree of freedom. Pero cuando el input está acá, tú lo puedes seguir moviendo y llega un punto, ahí ya no lo puedo mover más. ¿Sí? Sí, eso es a lo que a lo que quería llegar. In real life, if the input is through the slider, there will be a position in which you cannot move anymore because the links are aligned. And if you remember, I said that in mechanisms, when links get aligned, that's called it's something you need to avoid. Okay, so I need to avoid that. Then, how do we solve that problem in the motor of a car? Si ya les dije que en los motores de los carros hay un slider crank, pero el input no es rotacional, el input es lineal. ¿Cómo resuelven? Porque el motor no gira hacia un sentido y ahí se queda, ¿no? Está girando todo el tiempo. Aun cuando te vas al mirador romántico y quieres dejar la música, pues esta cosa está moviéndose, ¿no? Entonces, ¿cómo le hacen? A ver, los carrísticos de la clase, ¿cómo le hacen en el ensamblaje real para evitar que se atore ahí y que este link siga girando y el slider se regrese para el otro lado? O sea, si lo controlo de aquí no hay problema. Sí se regresa el slider, pero si el input está en el slider, ahí se detiene. ¿Cómo le hago?
Pues los pistones están puestos como, no todos van igualitos, pues están desfasados.
O sea, que se ayudan de los otros, ¿no?
Ujú.
Otro slider crank en el mecanismo no va a la misma posición y le ayuda al árbol de levas a seguir girando y a vencer esta inercia y seguir moviéndose. ¿Sí? Esa es una. ¿Quién lo dijo? ¿Fue Miguel, creo?
Sí.
Ok, esa es una manera. Hay otra manera en la que pueden evitar que se trabe aquí. En una aplicación real. Le voy a dar un
Yo
punto
pensaría que
extra. Ajá.
se pudiese usar algún resorte o algo así. No sé si es posible.
Sí es posible, pero no es esa la solución, la que estaba buscando. Hay algo en lo que no nos hemos metido porque hemos visto kinematics only. Pero la otra solución tiene que ver con, se las digo, ya no hay chance de punto extra. Acuérdense, el chiste es que cuando venga el input en el slider y llegue ahí, siga girando este link. No se me trabe ahí el mecanismo.
La gravedad podría ser que baje.
Más o menos por ahí va, más o menos.
Cargando una masa o algo.
A ver, explícame eso.
O sea, es que
¿Dónde
yo
le
veo que
agregarías? ¿Dónde le agregarías?
en la extremidad, digamos, en la punta.
El chiste es, interpretando lo que me dice Antonio, que cuando este venga aquí, que tenga una masa o algo que ayude a incrementar su inercia y que le siga.
¿No se
Sí.
podría poner algún tipo de imán también?
El imán y el resorte es como una solución como para jalarlo, entiendo yo, ¿no? Como que no se me quede ahí. Pero la solución que dice Antonio es, pues, ayudarle a la inercia de para que siga girando. ¿Sale? Si nomás hago un palito así como pues se va a trabar ahí. De hecho, la solución que yo tenía en mente, que me gustó más como la respondió Antonio, tiene que ver con la geometría de este link. Si solo es un elemento así de punto a punto, seguramente va a suceder esto. Pero si yo altero la geometría de ese link de tal manera que cinemáticamente no me afecte, o sea, que mantenga la distancia entre los joints, pero que la geometría sea tal que ayude a esa masa, ¿no? O le agregas la masa extra y se la pegas, o modificas o alteras la geometría de tal manera que tenga ese extra en una zona que le ayude a seguir girando, ¿vale? Eso no viene en el examen, pero es de las cosas que se topa el ingeniero en su daily life, ¿no? Por eso se me hizo interesante que pensaran en eso. Tune recording. Okay, let's try to solve then the position problem for this slider crank. For this exercise, for this lecture, we're going to assume that the input is in the link, not in the slider. Okay? So if you remember, we start by labeling things. So let's focus only on this mechanism. And I'm going to say that this is the input. I'm going to say this is theta 2 because this link is going to be R2. Okay, then that guy is theta 3 because this link is R3. And now I have an offset. I intentionally I drew the axis in which the slider moves at a certain vertical distance from the origin. Okay, so I have an offset here, and this offset is called R1. If the slider is moving in the same axis aligned to the origin, then R1 is equal to 0. Okay, and finally, I need a vector that is going to tell me where the slider is. So I need a vector that is going to tell me where the slider is, and that vector is going to be called R4. Those are my information I need to solve this. All I need to say to the guy that is reading this, or yourself, is that theta 2 is the input. Now, if I'm aiming to solve the position problem of the slider crank, so here is position problem, and I'm telling you that the input is theta 2, what can you get as output from this analysis? Which are the things we need to look for?
R4.
How far the slider is, so R4. What else?
Theta 3.
Theta 3. The only two remaining, right? It's not very hard. So theta 3 and R4 are the outputs of the position analysis of the slider crank. Okay, I always like to do this kind of diagrams because it allows me to think, okay, I know this guy, and by knowing this guy, because he has only 1 degree of freedom, I only need 1 input, then I can calculate everything else within the mechanism. What happens with R1? Why is R1 not an output of the position analysis?
Because R1 is not going to change.
Because it's constant. Exactly, because it's constant. Now let's build the vector loop equation. Let me just copy again the diagram. This time I'm going to draw the vectors on top of the mechanism. So I have R2. Okay. I have R3, R4, and R1. Right? And if those are my vectors, then how do I get my vector loop equation? What is going to be the vector loop equation?
R2 plus R3 equal to R4?
That one. I also need R1. So R2 más R3, remember that these are vectors, is equal to R4 plus R1. How do you know that? It's not hard to look at R2, R3, and that gives me this resultant, right? Which is also equal to R4, which is completely horizontal, plus R1, which is completely vertical. Okay? That's how I know that that's my vector loop equation. Now, what is R2, R3, R4, and R1 equal to? That's the next step. To fully express each of the vectors. Okay? So, let's express the vectors. R2 vector is equal to what? To its magnitude and what else?
Times the cosine of the angle.
Cosine, that's the horizontal component. And
Plus the sine of the vertical component.
that's vector R2. So remember, just a very tiny recap from physics. Magnitude, orientation. That's it, nothing else. In fact, I'm not going to leave that in the notes because I think it's not nice. Okay, so that's vector R2. Now what about, and that's only true if theta 2 is from the horizontal to the left. That's theta 2. Now, if I want to write a similar expression for R3, then I need to have theta 3 to be from the horizontal to the left. That's theta 3. Okay, now R4 or R1, whatever, which one you want to do first. I'm going to do R4. R4, and I'm going to write the same expression, same type of expression. And that's only true if the angle theta 4 is from the horizontal to the left. So from the horizontal to the left. In this case, it's very small, or is equal to, it's not very small, it's equal to what? It's completely horizontal, R4. So
Cosine.
theta 4 is equal to 0 degrees. If you substitute 0 degrees here, you end up having what? Sine disappears, sine of 0 is 0, and cosine of 0 is 1, so I end up having only R4I. And that means that R4 is completely horizontal. It doesn't have a component in the vertical axis. Now, something similar for R1. So R1 vector again is equal to its magnitude, some trigonometric functions. Now, in this case, theta 1 is equal to what? If I want to do that, use that expression, theta 1 has to be from the horizontal to the left. And in that case, it's equal to what?
90.
This is theta 1 is equal to 90 degrees. So 90 degrees. And if you substitute 90 degrees here, you'll have R1 in J. Okay. What I have to do now is use these expressions and substitute them in the vector loop equation. So I'll have R2 cosine of theta 2 horizontal, R2 sine of theta 2 vertical, plus R3 cosine of theta 3, R3 sine of theta 3, and all that equal to R4 plus R1. Yep. That's my expanded version of the vector loop equation. Which is the next step? Now that I have the expanded version of the vector loop equation, what do I need to do?
Separar los
Vertical
componentes.
and
Before we separate them in components, I need to identify what I know and what I don't know. And then I split them into components. So I don't remember which was the nomenclature we used last time, but I say circle the unknowns and underline what you know. And let's think about it. Now, what do you think about R2? Do we know it? That's the magnitude of the vector R2. That's the length of link 2.
yes,
So we know it. What about the magnitude of link 3?
Yes. Well,
What about the magnitude of the offset? The one that is constant.
Yes.
We
Yes.
know it. What about this, the angle of link 2, the orientation of link 2, which is inside of cosine of theta 2 and sine of theta 2? Do we know it?
yes, the
It's the
same.
input, right? So we know it. In fact, we should make a special mark for the input. Let me change color quickly. So that is input. Okay, now what about theta 3? The orientation of link 3, do I know it?
No.
That's an unknown. In fact, it's been written here in the tiny little diagram that we did. So this is an unknown. And of course, how far the slider is from the origin is another unknown. So I have two unknowns, and you know that you can get two equations from splitting in it into the components. So I'll do that now. So whatever happens horizontally is going to be here. So it is R2 cosine of theta 2 plus R3 cosine of theta 3 equal to R4. And then vertically at J, I have R2 sine of theta 2 plus R3 sine of theta 3 equal to R1. Let me try to do a better job for you with my handwriting. Okay, those are my two equations. Once I have separated them into vertical and horizontal components. Now, you can see that from the second equation, the only thing that I don't know is theta 3. If I carry on using the same nomenclature or the same convention of colors, I have the input. This I know, and this I know it. So the only thing I don't know is theta 3. So in this case, the solution of the system of equations is easier than for the 4-bar, because from the second equation I can work out theta 3, or in other words, de la segunda ecuación puedo despejar theta 3. So let's do that, okay? So theta 3 is equal to what? I'll have an inverse sine of R1 minus R2 sine of theta 2 over R3. And that's how I can calculate theta 3 once I know theta 2. Okay? How do I get theta R4? Sorry, how do I get R4? There's a very easy and simple way to do it, okay? And that is by simply substituting this guy, oh, sorry, different color, substitute theta 3 here, and the only unknown you have in the first equation is R4, so you can work out R4. Let me say all that again. Sorry. Lo voy a decir bien rápido. MATLAB, estoy usando como calculadora, menos 28 radianes de unidades. Listo, ya está lo de MATLAB. No, es que tengo que catch up with time. Entonces, length of link 2, we did say in MATLAB that it was a length of 10, so it matches with SolidWorks. Yeah, and if not, I can simply check in SolidWorks which is the length of R2 and go here and change the length. That's the beauty of this thing, right? Now let's check the length of R3. To check the length of R3, I'm going to open this part independently and check for its length. And it's 15. Yeah, you can see that the length is 15. Now the effective length between the joints. Okay, that's it. Bye. And you can check that this guy is roughly horizontal. Now, if you don't trust if this is horizontal or not, you can do the following. I have created a sketch, un croquis en este plano, and I'm going to use a line just to check if there is an offset or not between this central point and this central point. And if you can see, I have this symbol here, sorry. This symbol here means what? That is horizontal. So it is a line, so R1 is equal to 0. Okay. Now I need an input angle to validate my equation. And the input angle I selected for this example was, sorry, that's the wrong file, 45. Theta 2 is equal to 45. So when the input link, that is R2, reaches 45 degrees with respect to the horizontal, then the slider should be at 20.3 centimeters from the origin, and theta 3, and link 3 should be oriented at minus 28.12 or at 151 positive. ¿Sale? Now let's go to SolidWorks and check that. Here I am. Then I need to orient that guy at 45 degrees. Now I did my job before and this orientation is included here. So let me activate this. 45 degrees. How did I do that? Easy. I'm going to explain very quickly how do I do that. Relación de posición, and I select this bottom face, and then I select that bottom face, and I said put them at a certain angle right here, and I put 45, so nothing complex. So right now it's at 45, so this guy is not moving because I have intentionally put a 45-degree inclination, and if I'm right, then the length of this line should be 20 point something, if my calculations were right. So I go to calcular, medir. I don't know if, yeah, length of that line is 20.3 centimeters, you see? And MATLAB told me 20.29. Boom. You can add a boom there. Escríbanle ahí en sus notas. Boom. O como en los cómics. Porque si no salió y no siempre va a salir. Cuando salga, emocionense muchísimo. Bueno, siempre debería salir, right? Okay, so it matches. Length of R4 matches. Now let's check for theta 3. Now to check for theta 3, I'm going to draw another line just to help me measure. Let me check if I can do it without the line. So I'll measure with the orientation of that face with respect to that one, a horizontal one. And then you should be able to see this other window that is on the other screen. That's the other window. And it gives me 28.13. So it's also matching, right? Now you can also do by drawing a line if you want, or you can do a simpler way of validating this with lines because it's position. So I have a length of 10, length of 15, and a 45 orientation. So if my calculations are right, this is 20.3 again. And the theta 3 angle is from the horizontal. If I check the angle here, it will give me the negative one, 28.13 or 151, you see, from the horizontal. Up to you. You can do both ways of validating. But as I said at the beginning, this other mechanism is the one that you need to do for lab 3 and a slider crank. Okay?